Hello everyone, and welcome to this 2-video series on fault finding on DC circuits. This is for the 4001 course, and it should give us an overview on how to fault find and what the voltages and current should be on short and open circuits under fault conditions. Let's start with this circuit here. We're going to look at short circuits. We have a 50 volt power supply here. It's going to flow through two resistors, two 1K resistors, down lighten the bulb, down to earth. This is our circuit. Now what I'm going to do is introduce two short circuits. The first one here, the second one here. So in terms of voltages, we have a voltage drop across this top 1K resistor and a voltage drop across the second 1K resistor, and a small voltage drop across the bulb here. We have a uniform current of 24.7 milliamps. I'm now going to flick the switch here, and what that should do is it should offer the current an alternative pathway to this earth here. Okay, so I flick the switch. The first thing to notice is that the bulb has gone out, and the reason the bulb has gone out is because there's now no current flowing in this part of the circuit here, because current now has an alternative path to earth with virtually zero resistance. What difference does this make to current and voltage? Well, taking current initially, we can see it's gone from about 25 milliamps right up to 50. So we have an almost doubling of current here from the previous example. That's because there's now less resistance in the circuit, because we've removed this 1K kilo ohm resistor here. Also, it's worth noticing that we now have 50 volts here and 0 volts down here at this point here. So we've now dropped all of our 50 volt supply across that resistor there with our short circuit. So our current's gone up, and our current is taking a different pathway, not lighting the bulb. Going back to the circuit as it was, we can see that we've now got less current because it's flowing through two 1K resistors and the bulb, and we've got the steady example we had previously. Next thing we'll do is going to flick the switch here. This switch should actually short circuit only this resistor here. Okay, so current should now flow through the switch and bypass this resistor. This is the very definition of a short circuit, a bypassing effect on where the current is supposed to go. Now that I flick it, we can see the current takes the path. There's no current flowing through this resistor here, but there is now more current flowing through the bulb. We now have that nearly 50 milliamps back again. We can see we have a bulb which is far brighter than it was previously, and that's due to the increase in current. So if I just take this off here, we can see a duller bulb. Put the short circuit in, more current gives us a brighter bulb. Now, but in terms of voltage drops, most of the volts is dropped across the resistance here, 50 ohms here, and we've got 50 volts across that 1 kilo ohm resistor here, and we have 1 volt dropped across here, which is indicating a small amount of resistance in the bulb. So that's a summary of a short circuit. We have current going where it's not supposed to go, usually short circuiting a resistance of some description, and that leads to an increase in current flow in the circuit. Let's have a look at part 2 now, shall we? Open circuits. At the moment, I've got a closed circuit there with current flowing from a 240 volt power supply down to earth with 3 1 kilo ohm resistors and current at 80 milliamps. If we look at the voltages here, we can see we've got 80 volts dropped across this resistor here, 80 volts dropped across this resistor here, and 80 volts dropped across that resistor there. With current flowing, we expect this to happen, and we can calculate these things out using Ohm's law. But let's start by disconnecting and open circuiting the switch down here at the bottom. I click this. First thing that happens is we lose the connection between the 240 volt power supply, the ultimate connection, and earth. That means the bottom of the switch is connected to 0 volts. The top of the switch is electrically connected to the 240 volts. However, we can see now that we've got 240 volts at the top of the resistor, 240 volts at the bottom of the resistor. That means we have no potential difference between the top and bottom of the resistor. That means there's no current flowing. Same for this one here. We have 240 volts on either side, therefore we have no current flowing. If we look down here, therefore that point there has 240 volts. This point here has earth potential. That means the full 240 volts of that power supply is being dropped across the switch. Let's close the switch and let's open the next switch. Again, we now have the open circuit, so we lost that current flow that we had for a second while we were closing and opening the switch. But now look at where the voltages lie. At the top of the switch we have a connection to the top of the power supply of 240 volts. Notice again we've got 240 volts on one side of the resistor, 240 volts on the other side of the resistor. Therefore we have no current flowing in that top end of the circuit. If we look at the bottom of the switch, we'll see that everything's connected to earth, so we have a connection to 0 volts, but again we have the same potential difference drop across each resistor. 0 volts, 0 volts, 0 volts to 0 volts. That means there's no current flowing in this bottom circuit either. So we look closely, we see at this point here we have 240 volts, and at this point here we have 0 volts. That means we have a voltage drop of 240 volts between these 2 points, and that's where the potential difference lies in this circuit generated from the power supply. Let's just have one more look. Let's close the circuit, get the current flowing again. Back to where we were before, we now have 80 volts dropping across each of the resistors, and we have current flowing. Now, my final switch, click the switch, open it up again. We can see the top end of the switch directly connected to the 240 volts power supply, but at the bottom of the switch we have a direct connection to earth, but because we have no potential difference, we have no current flowing in any of these resistors. So where's our 240 volts dropped? It's dropped between the top and bottom of the switch. And these are the characteristics of open circuits. Anything that's connected to the mains supply or the supply has the positive voltage on it. Anything that's connected to earth has the earth potential on it, and the voltage drop is seen between the break in the circuit. Now, with this information, you should have enough to have a go at the 3 examples that are given to you in the book. Try the 3 examples and then see if you've got the right answer based on the circuits that I'm going to look through with you in a minute. Good luck.